So, in the last class we are discussing about the arithmetic group of instructions. So, in that we have discussed about the addition, subtraction, multiplication, division, and then we have discussed about this decimal adjust accumulator, decimal adjust after subtraction. Then we are discussing about some ASCII instructions AAA, AAS, AAM, and the last ASCII instruction is AAD. Even though here A stands for ASCII, the operation that will be performed here in AAD is BCD to binary conversion. BCD to binary convert before division. So, the remaining instructions they will be used after this arithmetic operations such as addition, subtraction, multiplication, whereas this is before division. Okay. So, here what happens is in this AAD, so this will convert unpacked BCD digits. I have already discussed what is unpacked, means only one BCD digit will be present in each byte. Unpacked BCD digits in AX, this implied register is AX, to its equivalent binary value in AL, this is also implied. So, this instruction basically converts unpacked BCD digits in AX into its equivalent binary value in AL. If I give an example, this will be clear. Suppose if you want to divide 67 decimal divided by 9 decimal say. So, what is the expected quotient and remainder? So, quotient will be 0.7 if I take unpacked BCD, this is unpacked BCD. And remainder should be 0.4. This is packed BCD. Now, if I want to perform this and if I want to get these results, okay, we will use this AAD instruction, and I will explain how this AAD instruction will be used to get the BCD quotient and remainder of BCD division. Okay. So, first I will take this 67 into AX register. So, we can use the move instructions. AX will be loaded with unpacked BCD. So, AX will be having AH and AL, this is AH and this is AL. So, AH we are going to take 0.6 and AL we are going to take 0.7, this is called unpacked BCD digit. So, the 67 packed BCD I am going to take in 2 8-bit registers in unpacked form 06, 07. Then if I write after taking this into AX register, if I write AAD, then what happens in AL? We will get the binary equivalent of this. So, what is the binary equivalent? So, the 67 decimal hexadecimal, if I convert into binary value 67, if you divide with 16, 16 4s are 64, 3 is the remainder, 16 zeros are 4, 43 H. So, 67 decimal is equal to 43 H. So, in AL 43 H will be present. This is about this AAD instruction. So, this AAD instruction basically takes two unpacked BCD digits into AX register. If I write AAD in AL, this binary equivalent means hexadecimal. Hexadecimal equivalent of this one will be stored in AL. Suppose if you want to perform this 67 by 9 BCD, so you have to load, move any register with CH with say 09D. It will take as hexadecimal. Then if I write div, as I have told, this is before division. So, here what happens is, what is the quotient and what is the remainder? So, in AL you will get contents of AL becomes the quotient which is 0 7 H, and contents of AH becomes 0 4 H. So, this is about the AAD instruction. I will explain again. So, this AAD instruction basically converts unpacked BCD digit in AX into its equivalent binary value in AL. So, binary in the sense here this is hexadecimal value. So, if I take the example of 67 decimal by 9, if I want to perform this BCD division, then this packed BCD we have taken to unpacked two 8-bit registers AH and AL, which is called AX. Then 9 you can take into any other register, then you can perform the division. But the thing is, this division instruction, the microprocessor instructions assumes the data that is given is in hexadecimal form, okay, but this is actually decimal. So, in order to convert this decimal into the equivalent hexadecimal 43, so we will use the instruction AAD. If I write the instruction AAD, the contents of AL becomes the hexadecimal or binary equivalent of 67, which is 43. Now, this will perform 43 by 9. So, because this 43 is the hexadecimal equivalent of this decimal, so this will give quotient and remainder as 7 and 9, and we know that in division div CH, we have to write div CH. So, in div CH what happens is internal operation of this we have already explained in the last class. So, AX contents will be divided with CH contents, okay. Quotient will be stored in AL and remainder will be stored in AH. So, this is about this AAD instructions. So, these are the different arithmetic instructions in 8086. The next group is logical group. Next group of instruction is logical, rotate, shift and compare instructions. So, in this group we will discuss about various logical expressions, rotate, shift and compare instructions. Coming for the logical instructions. So, what are the various logical operations we have? So, one is we can take the 1's complement of a number, or we can take the 2's complement of a number, we can take the OR operation between the two numbers, AND operation, exclusive OR operation. So, these are the various operations. Correspond to each operation we have the 8086 instructions. First, if we take the 1's complement, if you want to find out the 1's complement of a number, we have direct instruction which is called NOT. If I write NOT, we have to specify register / memory. So, this register can be either 8-bit or 16-bit, memory can be byte or word. Byte means 8-bit, word means 16-bit. So, whatever the register or memory that we are going to specify in the instruction, the 1's complement of that will be evaluated and it will be stored back into that particular register only. Okay. So, if I take the example, NOT, if I write AL, before the execution of this instruction, if AL contains is some 3FH. So, after this what happens is 3FH will be complemented. What is 3FH? Is 0 0 1 1 1 1 1 1. If you take the 1's complement of this, 1's will be changed to 0, 0's will be changed to 1, 0 0 0 0 0 0 1 1. So, this will be C, this will be 0. So, after this the contents of AL becomes C0. So, it simply determines the 1's complement of the register or memory location that is specified here. Again, wherever this throughout this 8086 instruction, wherever memory means the memory location that can be accessed by any of the addressing modes that we have discussed in the earlier classes. Similarly, you can take 16-bit register. So, if I take NOT BX, if BX contents is 0 0 FF, the complement of 1's complement of 0 is F, 1's complement of F becomes 0. So after this, contents of Bx becomes FF00. This is about the 1's complement. Similarly, we have instructions for the 2's complement. This is 1's complement plus 1. So the instruction for this one is negate, NEG. Not is for the 1's complement and negate is for 2's complement. Same format will be same as that. You have to specify either register slash memory. Register can be 8-bit register or 16-bit register. Memory can be a byte or word. This simply take the 2's complement of the register or memory. Register or memory. 1's complement is dash plus 1 will be stored back into register slash memory. Here all the flags will be affected, including overflow flag also. So there are some control flags which will not be affected by the instructions. So all the conditional flags will be affected by this particular instruction. So we can explain this similar manner. If AL contents is 3FH, if I write negate AL, then to 2's complement of 3F will be 0 0 1 1 1 1 1 1. 1's complement will be 1 1 0 0 0 0 0 0. 2's complement will be, you have to add 1. So this becomes 1 1 0 0 0 0 0 1. This is C1. So the contents of AL becomes C1. Similarly, we have the other logical operations such as OR and. So the next operation is OR operation, or the general format of OR instruction is OR. We have to specify 2 operands. So each operand can be taken in either register or memory. So we have register slash memory 2 comma register slash memory 1. In all these instructions, both cannot be memory simultaneously. Okay. So here we can have one of this one should be register. Say the register comma memory, or memory comma register, or register comma register. Memory to memory is not allowed. So in this instruction we have 3 possibilities. This can be register, source can be, destination can be register, source can be memory, or vice versa, or both can be registers. Both cannot be memories. So this basically this will perform register slash memory. 2 contents will be logically bit by bit ORed with the contents of this register slash memory 1. The result is stored back into the destination, which is memory register slash memory 2. Both cannot be memory simultaneously. Again, the memory means the memory location which can be accessed by using any of the addressing modes. If I give an example of this OR operation, if I write OR AH comma contents of say BX. So this is destination is register, source is memory. So before this contents of AH is something like 04H and contents of DS is 6000H and contents of BX is 5000H. Then the physical address will be DS into 10 plus this one 65,000. The contents of 65,000 memory location is some FAH. So here this operation is going to logically OR the contents of AH with the contents of the memory location which is pointed by BX register. So in this we have physical address of 65,000, in that 65,000 we have FA. So this operation will be AH contents will be logically ORed with the contents of BX. So AH contents will be 04 logically ORed with FAH. So if I take logical operation in terms of the bits. 04H is 0000, 0100, and FAH will be 1111, 1010, 10. So, bit by bit you have to OR. If both the bits are zeros, then only output is 0 for OR gate. If any one input is 1, output is 1. So, 00 means output is 0, this is 1, this is 1, 1, and anyhow these 4 are 1s. This will be F, this will be E. So, after the execution of this one, the contents of AH result is stored back into this destination register. In this case, this can be memory also, FEH. This is about the OR operation. You can OR the contents of any two registers, or you can OR the contents of register with any memory, and you can store the result back into either memory or register. Similarly, we have AND instruction, exactly similar operation. Here instead of OR, AND operation will be performed. AND register slash memory 2, comma register slash memory 1. So, basically the operation is register slash memory 2 is logically AND with register slash memory 1, and result is stored back to register slash memory 2. No need to give the example here. This is exactly similar to this OR operation, except that here instead of OR operation, AND operation will be performed. Similarly, we have exclusive OR operation also, XOR. Symbol for this one is XOR. Same thing, register 2 slash memory 2, comma register 1 slash memory 1. So, the same operation, the contents of register 2, both cannot be memories here also. In all the instructions, both cannot be memories simultaneously. Memory 2 will be exclusive OR with, this is symbol for exclusive OR, the contents of register 1 slash memory 1, and the result is stored back to register 2 slash memory 2. So, these are about 5 logical instructions: 1's complement, 2's complement, OR operation, AND operation, exclusive OR operations. There are some rotate instructions. The next group is here, rotate instructions. So, we can rotate the contents of any register or any memory location either to the right or left. So, we know that in digital, if I shift these contents towards the right by 1 bit position, so it will becomes division. If I shift the contents towards left by 1 bit position, that will becomes multiplication. This is the beauty of this shift operation. So, we can shift the contents of any register or any memory towards right or towards left by any number of the positions. First, we will start with a simple 1 bit rotate RCR. Rotate the contents of any register or memory through right along with the carry. So, this general format of this rotate instruction is RCR. After that, we have to specify register slash memory comma 1. If I want to rotate by 1 bit position, we have to specify here this one. And which location, which contents has to be rotated by 1 bit position? Contents of either register or memory. Again, this register can be 8 bit register or 16 bit register, memory can be byte or word. Okay. So, if I take the example of this, actually operation here will be, if I take byte operation. So, there will be total 8 bits. This is A0, A1, A2, A3. This can be contents of any register or memory, 8 bits. A4, A5, A6 and A7. So, there are totally 8 bits, and we will be having carry flag also. Suppose here the carry flag is stored. So, this is going to shift the contents of this one towards right by 1 bit position. So, in that the contents of A7 will be shifted to the A6 right position, A6 to A5, A5 to A4, A4 to A3, A3 to A2, A2 to A1, A1 to A0, A0 will goes to the carry flag and the carry flag contents will goes to A7. This operation is called through carry. This is called rotate operation through carry. Rotate, write, through carry. So, for example, if I take an example of this RCR some AH comma 1. Before this, if the contents of AH is some 80 AH. Now, what will be the contents of AH after RCR AH comma 1? Result will be stored back to this register slash memory. So, 8A is nothing but 1000 1010, and if I assume that the carry flag here will be initially set, then what happens is this will move to the carry flag becomes 0, the previous carry flag contents will be 1, that will comes here, that carry flag contents will come to here which is 1. So, this will move here, this will move here, this will move here, this will move here. So, like this. So, what will be contents now? After this, this becomes 1100 0101. This one, the last 0 has been entered into this carry flag. This will be contents of AH. These are the contents of the AH before the rotate instruction, and this is after rotate instruction. And what happens to carry flag? Will be reset. So, this will be C5. So, contents of AH will be C5 and carry flag will be reset. This is how this rotate instruction will be executed. So, the contents of 16-bit register, the similar operation will take place. The contents of A15 will become the contents of carry, and A0 will be in any case will transfer to the carry flag. Okay. Similarly, we can have this as a byte from the memory location or word from the memory location. This is if you want to shift by 1 bit position. If I want to shift by 4 bit position, instead of writing this 4 times, we can directly mention that 4 into a register called CL, which is implied register. So, for multiple bit rotations, for single bit rotation we have to mention 1, for multiple bit rotation you have to write RCR register slash memory comma CL. So, whatever you have to store in CL, that many number of times the contents of this register or memory will be rotated to the right, RCR. So, exactly same operation, but here this CL, if I take the example of this one, if I take the same example, say AH is having some 8A and carry flag is set. And if CL is having say some 4, then this will rotate 4 times. If I write RCR AH comma CL, then after this operation will be 8A is equal to 1000 1010 and carry flag is initially set. This is AH contents, this is carry flag contents, this was initially set. So, after one rotation, what will be the contents of this one? As I have explained in this previous class, the contents of carry will come here and each bit will move towards right by 1 bit position. So, this becomes 1 1 0 0 0 1 0 1, carry becomes 0. This is after one rotation. After second rotation, again this carry flag will comes here 0 1 1 0, and this all bits will be shifted to this one 0 1 1 0. So 0 0 1 0, this carry becomes 1, this 1 will be shifted to here. After third rotation, so all these bits will be shifted here, this will become 0 1 1 0 0 0 1, and this 1 will becomes carry, this 1 becomes this. And after fourth rotation, so this previous carry flag 1 will come here, so 1 1 0 1 1 0 0 0, and this 1 becomes this. So after this instruction, the contents of accumulator AH will be, this is D and this is 8, and carry flag will be set. So AH will be having D8 and carry flag will be set. This is how you can rotate the contents of any register or memory by multiple number of the bits. The number of bits time that has to be shifted has to be taken into CL, and this is default register, you cannot take into any other register. So CL contains the number of rotations to be done, and we have to specify here a register or memory location. This is about RCR, register slash memory CL. Similarly, we have, this is right operation, we have left operation also. We have two instructions for left. RCL, register slash memory, we can shift by 1 bit position. The contents of either this register or memory will be shifted to the left by 1 bit position through carry. This is through carry. Okay. And we can have RCL, register slash memory, comma CL. If want to rotate through carry the contents of register or memory to the left by CL number of times. So there are about 4 rotate instructions through carry. So 2 instructions will be for single byte rotation and the other 2 instructions will be for multiple byte rotations, but all the 4 instructions will be through carry. And if you want to perform this rotate operation without carry, there are 4 more instructions which will be ROL. They correspond to RCL, there is an instruction called ROL. The same format, register slash memory, comma 1. The difference between this RCL and ROL is, in case of ROL, this is A0, A1, A2, so on. So this will be rotated to the left. So A0, here somewhere carry flag will be there. So this A0 will goes to A1, A1 to A2, A2 to A3, A3 to A4, and so on. In case of RCL, the contents of A7 will go to carry, the contents of carry will go to A0, whereas in case of ROL, the contents of AC will go to C carry flag as well as A0. Okay. This is only difference. In case of RCL, this A7 will goes to carry, the carry contents will goes to A0, whereas in case of ROL, A7 will goes to carry as well as A0. Okay. So if I take the example of the same 8A, and similarly we have RO, R, register, comma memory, comma 1. So this is exactly same this operation, but the contents will be passes without carry. Okay. So if I take the same previous example, and if it is ROR, so if I take this instead of RCR, if I have ROR, what will be the contents of this AH register after this, if carry flag is set before this? what will be the contents? The same operation. So, the contents will move here. So, this will move into the carry flag as well as this. So, what are these contents? The last contents 0 is moving to here as well as here. So, what happens is here this becomes 0, this is 8 is 1 0 0 0 0 1 0 0 1 0 1 0 and carry flag is anyhow 0. So, this content becomes 4 A. The contents of AH becomes 4A and carry flag will be reset in both the cases. If this is ROR AH comma 1. Now, I think you understand the difference between RCR and ROR. So, the contents of the last bit will goes to LSB bit will goes to carry as well as MSB in case of ROR, whereas in case of RCR the contents of LSB bit will go to the carry bit will goes to the MSB position. This is for single bit rotation. We have multiple rotations similar to this, we can have write CL. So, the two multiple byte rotation of contents of register or memory, we can write ROL register slash memory comma CL, this is without carry, ROR register slash memory comma CL. So, they are for rotating the multiple number of times. So, they are the different rotate instructions. So, we can rotate through the carry, without carry also. We can rotate by only one bit position or we can rotate by multiple number of bit positions. Similarly, we have shift operation. The next one is shift operations. SAL register slash memory comma, you can rotate, you can shift by one bit position or you can shift by multiple bit positions similar to the rotate instruction. So, this is also exactly similar to the rotate instruction except for the difference that, so here the also register can be 8 bit or 16 bit, memory can be byte or word. So, if I take a simple byte shift operation, and this is shift left, A stands for left. So, this diagram will explain the operation of this SAL. This is A0, A1, A2, A3, A4, A5, A6, A7. So, in case of SRL, we are going to rotate RLL. So, if it is a, instead of shift, if it is a rotate operation, same the contents of A0 will move to A0, A1 to A2, A2 to A3, A3 to A4, A4 to A5, A5 to A6, A6 to A7. Here also the same operation, but the only difference here will be the contents of this A7 will be in case of shift operation, this will move to carry flag. Whereas in case of rotate instruction, in one case this A7 will goes to A0, in other case the carry flag contents will goes to A0. Whereas in shift operation this is open loop configuration. In case of rotate we have closed loop, whereas here we have open loop. Here so many zeros will be added, A0 will be fed with zeros if this is 1. Okay. So, now to understand this operation, so if I give an example, suppose if say same AH is equal to 8A, if carry flag is set, if I write SAL AH comma 1, then 8A will be 1 0 0 0 1 0 1 0, and if you rotate left by one bit position, so this becomes this 0 here, and here so many zeros will be added. So, this 0 will move here, this 1 will move here, this 0 will move here, this 1 will move here, this 0 will move here, this 0 here, this 0 here, this 1 will be moved to the carry flag. Initially also carry flag set, now also it remains set. Now here so many zeros will be added. So here this position will be loaded with zeros. So this becomes 1, 4. So the contents of AH becomes 1, 4H and carry flag will be anyhow set. This is about shift left operation and how this will be different from the rotate left operation. So in rotate left operation what happens is the contents of A7 will move to C carry flag and then carry flag to the LSB or A7 contents to the A0. Whereas here so many zeros will be added at the A0 position. Similarly, if you want to shift by multiple positions, so if I have this SAL register comma memory comma CL. Here also you have to take this number of times the shift operation to be performed in CL, that CL has to be mentioned here. So this is for single bit shift, this is for multiple bit shift. Similarly, we have two shift right operations, one for 1 bit position, another for multiple bit positions. This you have SAR register slash memory comma 1. Here there is some slight difference is there between the shift left operation and shift right operation. If I take say byte only, same byte operation, this is A0, A1, A2, A3, A4, A5, A6, A7. So the contents will be shifted to the right position. Okay. So A7 will goes here, A6 will goes to A5 and so on. This will go to the carry flag. In case of left operation, so many zeros will be inserted at A0, whereas here the contents of A7 itself will be loaded into A7 also. MSB bit is simply copied. Okay. Instead of inserting the zeros in case of shift left operation, here the contents of A7, the MSB bit will be moved to the MSB bit. So simply MSB bit will be copied. This MSB bit will be this bit as well as this bit. Okay. This is the main difference between shift left operation and shift right operation for single bit position. We have similarly for multiple bit position, we have SAR register slash memory CL. In all these shift operations and rotate instructions, CL is by default stores the number of bits to be shifted or rotated. Okay. So if I give an example of this SAR1, if the contents of AH is same, say 8AH, if the carry flag is initially reset, say if I write SAR AH comma 1, so what will be contents of this one? 8 will be 1000, A will be 1010, carry flag will be, this is AH, carry flag is set, this is before the instruction. After the instruction what happens? This 1 will transfer to here, 0 to here, 0 to here, this 0 here, this 1 here, 0, 1, this 0 will goes to this carry flag, the same 1 bit will be copied here also. Okay. So this becomes C5 and carry flag is reset. AH will be C5 and carry flag will be initial also reset, now also because the latch bit is 0, initially this carry flag is set. If I take this as set, then now it will be reset. Okay. So this is about shift right operation. The only difference is instead of inserting the zeros in case of left operation, in shift right operation the same MSB bit will be copied. That is the difference between shift left and shift right operations. So, there are 4 shift operations, 2 shift left, 2 shift right. So, 1 bit position or multiple bit positions. And the last instructions in this group is compare instructions. This is also one of the important operation. So, in compare instruction, this is general mnemonic is CMP, compare. Then we can have register slash memory 2 comma register slash memory 1. We can compare 2 registers. Here also memory to memory operation is not allowed. Memory to memory comparison is not allowed. So, one must be register. So, we can compare one register contents with one memory, or we can compare 2 register contents. Okay. So, the basic operation here will be, this is exactly similar to the subtraction operation. Register slash memory 2 contents will be subtracted from register 1 slash memory 1. So, the only difference between this and subtraction is, in case of subtraction, the result will be stored back into this destination register or memory, whereas here the result is discarded. So, this will be performed, but result is discarded. Now, based on this result, so it will set or reset the flags based on the result of the comparison. Flags will be affected. So, based on this we can compare 2 numbers. Okay. If carry flag is set, means there is a borrow, so this number is lower than this number. If carry flag is not set after this comparison, then what does it mean? The first number is greater than second number. If 0 flag is set after this operation, means both the numbers are equal. So, like that we can compare which number is larger, or whether these 2 numbers, given 2 numbers are equal or not, through this compare instruction. But in case of subtraction, the result will be stored back into the destination register or memory, whereas in case of compare, the result is simply discarded, except for that there is no difference. Okay. Only result is discarded here. In case of subtraction, result is stored. And we can compare directly with a data also, immediate data. The second compare instruction is register slash memory contents with data. So, we can give 8 bit register or 16 bit, memory can be either byte or word. We have to use correspondingly the data which can be 8 bit or 16 bit. If you give 8 bit register, data also should be 8 bit. If I give 16 bit register, data must be 16 bit. If I read a byte from the memory location, data size should be 8 bit. If I read a word from the memory location, data size should be word, which is 16 bit. So, these are about different compare instructions. Okay. So, the next group of instructions is branch instructions. If the microprocessor control transfer from one place to another place, then we have to write the branch instructions. There are 2 types of the branch instructions. One is called conditional, another is called unconditional. As the name implies, unconditional, without checking any condition. So, this will branch to a particular location. So, the examples of unconditional are, simply we can write jump, JMP, comma, we can specify register slash memory. So whenever the microprocessor executes this instruction, simply the instruction pointer will be loaded with the register contents. The instruction pointer will be simply loaded with the contents of register slash memory. So we know the purpose of this instruction pointer, which always holds the 16-bit offset from the starting of that particular segment to the which is to be executed next. Okay. This always holds the address of the instruction, address in the sense here only the offset, the address of the instruction which is to be executed next. Okay. If you want to execute the instruction which is located at this particular address, then you have to write simply jump comma that address. If I take an example, jump JMP some BX, if BX contains is 5000. So if the microprocessor is executing, I will come to the conditional instructions later. Okay. So this is code segment, microprocessor is executing the instruction one by one. This is starting of code segment, say some 60,000 H. Suppose the microprocessor is executing this instruction. So this is jump instruction, jump BX. If BX contents are 5000. Suppose if this is there in something like say 63,000 H. So what is the offset here? The next location is 63,001. Okay. So the offset from here to here will be, here to here offset will be 3001 H. This will be held by instruction pointer. The instruction pointer contents becomes 3001 H, which I have explained in the earlier classes also. So the instruction pointer always holds the address of the instruction which is to be executed next. So this instruction needs to be executed next. If this is not a jump instruction, so the microprocessor is supposed to execute this instruction. What is the offset of this instruction is 3001, that will be held by instruction pointer. Suppose if I want to skip this instruction and if I want to execute the instruction which is located at some other location which is say some 65,000, then how does this microprocessor after this will jump to this particular instruction? For that the instruction pointer has to be loaded with. So what is the offset of this address from this starting is 5000. So this instruction point, simply if I load this with 5000 H, then this will skip all these instructions in between and it will jump to the instruction which is located at 65,000 H. Okay. So this is how this jump instruction will be takes place. So whatever the previous contents of the instruction pointer will be now replaced with the address which is specified in the register, so that the microprocessor control will transfer to that particular instruction. Here this can represent a memory also. Okay. This is about unconditional, without checking any condition, it simply jumps from that particular instruction to the offset which is specified in the instruction itself, to the memory location whose offset is specified in the instruction itself. This is about unconditional jump. And there are some conditional jumps. So it will check first some condition. If some condition is satisfied, then only it will jump, otherwise it will simply neglect that jump instruction, it will go to the next instruction. So we have different conditional instructions that we will discuss in the next lecture.